Welcome. In this video, let's explore the concept of deadlock prevention. We will learn how to prevent deadlocks by focusing on the necessary conditions that lead to them. The main idea is to prevent one of the required conditions. For a deadlock to occur, four conditions must be present simultaneously. These are mutual exclusion, which means that resources cannot be shared. Hold and wait, where processes hold allocated resources while waiting for additional ones. No preemption, which implies resources cannot be forcibly taken away from a process. And finally, circular wait, where we have a circular chain of processes each waiting for a resource held by the next process in the chain. When these four conditions hold true simultaneously, a deadlock can occur. To prevent deadlocks, we can target the four necessary conditions and try to negate at least one of them. The first approach is addressing mutual exclusion. The goal here is to make resources shareable whenever possible, thus eliminating the need for exclusive access. The second approach is tackling hold and wait. We can require processes to request all required resources at once before execution begins. The third approach is resolving no preemption, which involves allowing resources to be forcibly taken from processes when needed, especially by higher priority processes. The fourth and final approach is breaking circular wait. This can be achieved by imposing a total ordering on resource types and requiring processes to acquire resources in that specific order. Preventing any one of these four conditions is enough to prevent a deadlock from occurring. One way to prevent deadlocks is by targeting the mutual exclusion condition, which occurs when resources cannot be shared. A key strategy here is to use shareable resources whenever possible, like read-only files or shared memory. Implementing spooling for devices like printers, which allows multiple processes to submit print jobs without directly competing for the printer. The operating system can use virtual resources instead of physical ones to allow multiple processes to use same resources. Designing data structures to allow concurrent access can minimize the need for exclusive locks. Implementing fine-grained locking mechanisms, such as record-level locking in databases, can reduce contention and allow multiple processes to access different parts of the same resource concurrently. To prevent the hold and wait condition, the idea is to ensure that processes do not hold allocated resources while waiting for additional ones. One approach to achieve this is to require processes to request all resources before execution begins. This way, a process either gets all the resources it needs, or it waits until all of them are available. Another approach is to make a process release all resources before requesting a new set. By releasing all current resources before requesting more, the process avoids holding resources while waiting. Resources can be allocated only when none are currently held, ensuring that processes do not hold some resources while requesting others. Two-phase locking protocol can be used, where a process first acquires all the locks it needs, and then performs its operations, releasing all locks in the second phase. Allowing preemption means that resources can be forcibly taken away from processes when needed. Resources can be forcibly taken from processes to prevent deadlocks. A higher priority process can preempt resources from a lower priority process. Implement priority-based preemption, where processes with higher priorities can preempt resources held by lower priority processes. Use rollback mechanisms to restore process state. If a process loses resources, it can roll back to a previous safe state. Checkpointing can be applied for recovery after preemption. Processes can periodically save their state, so they can resume from the last checkpoint if preempted. To prevent circular wait, we can use the resource ordering approach. A common way to implement this is by assigning a unique number to each resource type. Require processes to request resources in ascending order. Enforce global ordering of resource acquisition to prevent the formation of circular dependency chains. Here is an example of resource ordering. If a process needs resources 1, 2, and 3, then we acquire resource 1, then acquire resource 2, then acquire resource 3. This ensures that circular wait will not occur. Each deadlock prevention approach has its own advantages and disadvantages. Mutual exclusion prevention is simple to implement for shareable resources and has no performance overhead, but it is not applicable to inherently non-shareable resources and may require complex concurrency control. Hold and wait prevention is conceptually straightforward and works for all resource types, but leads to poor resource utilization and processes may wait a long time for all resources. Preemption allows for priority-based scheduling and can resolve potential deadlocks dynamically, but introduces overhead for saving and restoring process states and is not applicable to all resource types. Resource ordering is relatively easy to implement and has no resource utilization penalty, but it requires global resource numbering and may force non-optimal request ordering. The choice of which prevention strategy depends on specific system characteristics, the types of resources, and the overall performance requirements. To summarize, remember that deadlock requires 4 conditions to occur simultaneously: mutual exclusion, hold and wait, no preemption, and circular wait. Prevention strategies aim to eliminate at least one of these conditions to avoid deadlocks. Each prevention approach has trade-offs in resource utilization and system performance. Resource ordering is often the most practical approach due to its relative simplicity and minimal performance overhead. Next, you can explore deadlock detection, deadlock recovery, and deadlock avoidance algorithms. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.